Welcome. In this video, we're going to look at RSA, and just an historical note, it's named after its inventors, last names of Rivest, Shamir, and Edelman, and so just that's kind of where it comes from, so that's kind of fun. But the idea here, and we kind of saw this last time we were all together and discussing Euler's formula, Euler's formula, with modular arithmetic, but we have P and Q as large primes, and we take n, which is the product of those two, or n factors into P and Q, and then we have C and E as integers. It says the problem here that we really want to be able to solve is that we have this x to the E is congruent to C modulus n, and then we want to solve that for x. And so in theory, what we really want to have happen is that it's easier for Bob to solve because he knows P and Q. But then if Eve, who is eavesdropping, right, this should be hard since P and Q is not known. So again, with most modern technology, we can compute n, or we can factor n fairly quickly. Go to Wolfram Alpha, type in factor, number, boom, hit enter, done. Okay, but now if you're n is something like 10 to the 50th digits, well, then that becomes a little bit trickier to solve. So this actually leads to the dichotomy that we often see, is that if you have the information, so with info, it is easy, and conversely, if you don't have it, so without the information, it is hard. Okay. So that's what we're going to see when we go through this process. Now, maybe you're familiar with RSA, maybe you're not. I'm just going to go over this process. In the next video, we're going to look at an example. Okay, so again, the setup we kind of outlined, but here's the details. So we want to pick primes, P and Q, and have those primes such that n is n factors into those. We choose E, and this is the condition that we have on E. Okay, that looks a little familiar. Maybe we need to remember where that comes from. Okay, and so we're going to publish n and E publicly, and then we need to choose plain text. Okay, and then we use the public key to encrypt the plain text, but just by doing m, whatever our plain text is, to the exponent that's publicly available, mod capital N, and then we get this C and we send it off. Okay, and then for the receiver, when we're trying to decrypt it, okay, we already know E and we know N, right? But then we're going to compute D with this particular modulus, P minus 1, Q minus 1. And now, again, to a bystander, to Eve, P and Q are not known, so P minus 1, Q minus 1 would not be known either. But anyway, once we have D, then we can decrypt this mod, or as C to the D mod N. And so really here, E is called, the reason it's called E is it's called the encryption exponent. And then D is called the decryption exponent. Decryption exponent. And then at the end of all this is, so we should get m is equal to m prime. Or rather, the message that we receive from decryption is the message that we have from the beginning. Now, why does this all make sense? Well, that is where I want to ask you a few quiz questions. So stay tuned for those.